Hey guys, so this is our team. My name is Nader Shah.
I'm Zaid. I'm Daniel. I'm Jacob. And I'm Mohammed.
So the objective of our proposed measurement system is to first measure the displacement of different masses, which are all relative to certain points. Using different sensors, we hope to be able to create a system that can increase or decrease to any height to an inputted line.
For our measurement system, we're using 3 different sensors, which are an accelerometer, proximity sensor, and a limit switch. The goal of accelerometer is to measure the acceleration of an object, which can be found by examining the forces acting on it. These forces can be static, like gravitational forces, or dynamic ones, like moving or vibrating the sensor. Some accelerometers work by using piezoelectric crystals, which generate a voltage in reaction to the acceleration forces, while others use capacitors, which when moved changes the capacitance, and the resulting force and acceleration can be found from it.
A proximity sensor is a sensor that is able to detect the presence of nearby objects without any physical contact. These sensors emit an electromagnetic field or an infrared light that is bounced back to the sensor. If the sensor detects any changes in the return signal, it will be triggered. Proximity sensors today are commonly found in our smartphones, normally to turn the screen off when the user brings a phone towards their ear. A limit switch is a switch operated by the motion of a machine part. It can choose between 2 different paths when it's activated, much like a light switch. Limit switches can perform simple tasks such as turning a machine on and off, or much more complex ones such as counting passing objects.
So our group envisioned that the design would consist of an accelerometer, either proximity sensors or limit switch, maybe 3 or 4, the SRVO2, and then something to support the masses such as the spring or string. We were hoping that it would look something such as the SRVO2 was turned on its side, hanging off of a table. Then the proximity sensors or the limit switches would be placed along the side of the table so that it'd be able to measure the displacement, or it'd be able, as the mass is displaced, it would stop at each point. We would attach the accelerometer to the SRVO2 so that it would be able to measure the angular displacement as the mass is first hung at a certain distance and then as we drop it. The spring or the string would allow us to place or use different sizes of mass so that we would further be able to prove the functionality of our device, because as we know, the more mass, the more it's going to fall. The less mass, the less it's going to fall from a certain height, right? If we put a larger mass here, it's going to fall further down, whereas if we play a smaller mass from here, it's going to fall a less amount. And so the spring, it would be ideal for us because then it'd be able to allow it to stretch more, whereas the string, we know that it would all land at the same point. We were also hoping that we would be able to program the accelerometer so that it would be able to measure the angular displacement as it was dropped, which would then allow the program to automatically understand how much more, or due to how much more mass was placed, how much more it needs to raise in order to get to that first, second, and third stop. From this, we might also be able to program the device so that it can determine how fast or slow to be able to raise that mass in order to ensure that it doesn't sway or it doesn't bounce around a lot. Because if we're going to use a spring, we know that if we raise it too fast and stop it, the machine or the mass is going to start going like this on a spring. So if we were able to use the accelerometer and program it so the mass would, or the device would also automatically know that, okay, there's 5 kilograms, say we can only move it up this quickly so that it doesn't sway around and it doesn't bounce. The one research application would be to enhance our knowledge on stress for wires or something, or springs like we're probably going to use. And so from that research, we would then have a better understanding for things like cranes or even elevators, that we know how much possible stress or how much weight we can put on these before the strings will snap.
There are many real-world applications present for lifting mechanisms, most of which are related to elevators. Passenger elevators are used in buildings and are designed to move people between floors of a building. Express elevators are designed to move people from ground floor to a sky lobby, skipping several floors in between at a high speed. Wheelchair or platform lifts are a specialized type of elevator designed to move a wheelchair. Freight elevators are meant to carry heavy loads. On aircraft carriers, elevators carry aircraft between the flight deck and the hangar deck for operations or repair. Pulley lever systems and construction cranes are also examples of real-world applications.